Okay, welcome, and we'll get started here in just a second. We're going to continue on in chapter 21, I think it is, here with nuclear chemistry. Like usual, if you have a question, feel free to ask it down below or wherever your chat box is there, and we'll definitely get those questions answered for you. And again, we'll be picking up here where we left off in chapter 21, which is our nuclear chemistry. Okay, so we're continuing on here, and reminder we're gonna have lecture obviously like normal, and then we will be doing our presentations today, starting during our lab time with the order there that most people signed up for, and you'll be able to obviously do your presentations during our lab period at 11:30 or starting at 11:30. Okay, so we've been talking about nuclear chemistry here in this chapter, and remember that sort of nuclear reactions are different than general sort of chemical reactions in a few different ways. One major way is it deals with really the particles that we find in the nucleus, and that is very different than those reactions that we find uh, in a normal chemical reaction where we're just dealing with really electrons. So here we're kind of fundamentally changing the components of the nucleus, and that obviously involves a lot of energy to do that. And also a very important difference is what we see is no conservation really of elements. So because we're changing the number of protons, which essentially defines a element, if you will, um, we are going from one element to the next. So we talked about different ways or different types of sort of radioactive reactions. A lot of them do involve some type of decay process, and that usually involves emitting a particle. That could be an alpha particle, as we saw, which is like helium. It could be a beta particle, a positron. It could be gamma as well. Uh, and when they do release these particles, really these particles are released as those sort of protons and neutrons in the nucleus sort of gets converted into other things. These particles are given off. So when we balance nuclear equations, a little bit different than normal chemical equations, what we're looking for is really the balancing of the mass number on both sides. So when you add up the total mass number on each side, they do need to equal each other. And the total atomic number on both sides also need to equal each other as well. Um, and again, sometimes things would be missing from an equation. You might have to figure out what's sort of the missing element. And again, it is that atomic number that you can find on the periodic table, which is the number of protons that will help you determine sort of the missing element. We also talked about decay series as well. A decay series, again, is really a series of reactions that occur until sort of a stable nucleus is achieved through this process. And I think we looked at sort of the decay series of uranium there. And again, you really could do a decay series the same way as you sort of do balancing equations. You could write each individual equation for each decay process. Essentially, the product of the first decay will become sort of the reactant in the next one, and you sort of continue that pattern until you go through it. You could either kind of write them all out like you're balancing equations, or again, if you're sort of just interested perhaps in sort of your final product that you'll get as a result of a bunch of sort of decay processes in a row, you can kind of use that little kind of quick math where if you have an alpha decay, you take 4 away from the mass number for each one, and you take 2 away from the atomic number. While if you have a beta decay process that occurs, you basically add 1 back to the atomic number. So again, you can kind of get to the end result really quick. It's also a good way to, if you sort of do it individually, sort of step by step and write out the reactions to sort of double check your answers at the end to make sure you did get to the right one. And the last sort of thing, a couple of other things that we talked about as well in this chapter is stability. Again, a couple of different ways we can look at stability. Number of protons and neutrons in terms of are they even or odd. Again, even for those things. Protons and neutrons is sort of the best situation. Also, the neutron to proton ratio, the N to Z ratio, is another way that you can look at stability. And again, depending on sort of the atomic number as to where that sort of stability lies in that belt of stability, that valley of stability that we saw in that graph. And last time we finished up talking about sort of kinetics of radioactive decay. So all radioactive decay essentially will follow first order kinetics. So those are the same first order integrated rate laws that we saw when we talked about just straight old regular chemical kinetics. They're the exact same things, exact same formulas. So that's your natural log of A equals your natural log of A naught minus KT, and your half-life equals the natural log of 2 divided by K. Again here, pretty much the same, except a few slight differences in sort of how we used them when we did really chemical kinetics. Again, in nuclear chemistry, sometimes they like to use different symbols that kind of represent the same thing. So again, instead of the rate constant, usually it's referred to as the decay constant. And again, sometimes they'll use some different symbols for that. They may use the lambda symbol for it. They obviously will use K and just call it the decay constant. In addition, instead of sort of the natural log of A, they'll sometimes use the natural log of N to refer to a nuclide. And the main difference, though, is a lot of times in chemical kinetics, we use concentrations in terms of those guys. You don't have to use concentrations. Again, you could use something like grams, milligrams. You could use some type of radioactive decay in terms of a rate of decay that we'll see here in just a second. But again, you can use some different units, if you will, for the concentrations. Any questions on any of that stuff that we talked about, I think, the last couple of times here in this chapter? Okay, so I think this is where we left off. So why don't you take a minute or two here and see what you come up with. Radon 222 is produced. If there is 10.24 grams in the house today, how much was there 5.4 weeks ago? The half-life of it is 3.8 days. So take a minute or two here, see what you come up with, and then we will talk about it. Okay, let's take a look here. So again, like I said, all radioactive decay really follows those first order kinetics, and really there's two sort of laws, that formulas that we've seen. Natural log of A equals the natural log of A naught minus KT. Again, here in nuclear chemistry, they may use a slightly different symbol sometimes, but it's really the same formulas. And our half-life here is the natural log of 2 divided by K. So in this case, we want to know how much is going to be there after 5.4 weeks, and we're just given the half-life. So we have the time. We want to know how much is going to be there, and we were given our initial. So like I mentioned before, very common, you do need to figure out the decay constant here, and that means that you oftentimes will need to use this sort of half-life equation with it. So we're going to do that to find our decay constant. So if we rearrange that, the decay constant would be the natural log of 2 divided by the half-life. And that would get us the natural log of 2 divided by 3.8 days. And if we do that, 0.182, it looks like here, 0.182 days. And again, the units here are really important as well, because the units here tell us that they are in days, and much like normal kinetics, our time though is in weeks. So we do have that difference in units, and we do have to do some type of conversion. So since I have my decay constant in days, I'm going to convert my weeks into days here from time. So in a week, there hopefully should be 7 days, I think. And if we do that, we get 37.8 days. And again, just like normal when we're using this equation, we do want to watch these two in terms of those units, right? So now we have pretty much everything that we need here to basically solve this. So if we take the natural log of A equals the natural log of our initial, which was 10.24 grams, minus our K, which we found, times our time here, which again we converted into days as well, so everything should cancel in terms of days. The units here are grams, which is what we're going to end up with. So if we kind of clean up the right hand side there, we will end up with the natural log of A equals minus 4.5532-ish. We're going to take the E of both sides. And that's going to give us our sort of final concentration, if you will, of 0.011, we'll call it. 0.011. And again, the units here are going to be grams because our original units here were grams, right? And again, it does make sense. We are going through a decay process, so we should definitely end up with less than what we started with. Any questions on any of those steps there? So again, it really is just sort of the same kinetic sort of problems that you've done before. But I would say probably more so in these because it does involve nuclear decay. A lot of times you're just given the half-life. So more so in sort of these type of problems, you definitely have to use that half-life equation in connection with the integrated rate law a lot more than maybe you did in just a basic chemical kinetics type problem. Any questions on that there? Okay. Now, we could also use sort of these kinetics as well to do things like radiocarbon dating or sort of nuclear dating to basically figure out how old something is. So it's a very common sort of calculation that's done. So for example, we could use carbon there and figure out how much carbon-14 is sort of there, or how much nitrogen was developed over a period of time. Again, the carbon-14 half-life there is 5730. You can also do uranium as well. So sometimes uranium dating is done. And again, the half-life there for uranium, as you can see, is 4.5 times 10 to the 9 years. Again, these are very, very um, long periods of time, obviously. And again, sometimes people look at it in terms of how much lead perhaps appeared or how much nitrogen appeared, but most people just sort of do um, the carbon 14 and the uranium. And again, really to figure these out, you're still going to use those same equations that we just saw, which is our first order kinetics. The difference in sort of these radio dating type problems, you're usually solving for T, which is time in most cases. Not 100% of the time, but a lot of times you'll kind of obviously solve for time to figure out how old something is. And just like previously, you will a lot of times have to use your half-life equation with it. So why don't we take a look at one? Why don't you give it a try, see what you do here. So an ancient skull gives 4.5, and that's disintegrations per minute per gram of carbon. So this right here is a unit of radioactive decay. And this is not Celsius, this is actually carbon. And that's disintegrations per minute per gram of carbon. And why that's important is because it's carbon, it means that you're really dealing with this. And you should use the half-life for carbon, okay? So why don't you give it a try here and see what you come up with. Oops. And again, that was a case you missed it there, 5730 on the half-life. So if a living organism gives 15.3 disintegrations per minute per gram of carbon, how old is the skull? So again, you want to use your kinetics equations. And again, here we're not using molarity or grams, we're actually using rates here of radioactive decay. Again, works the same way. So why don't you take a minute or so and see what you come up with. Okay, so let's take a look. So again, we're going to use the same equations, and we're going to have our natural log of A equals natural log of A naught minus KT. And again, our half-life here, natural log of 2 divided by K. We are actually given in this case our initial and our final, or backwards when I say that. We're looking again here for time. So again, very common in these, we are missing the decay constant here. So that's why we do need to know our half-life. And again, that's why this is important. Sometimes people see the big C, and again, they just automatically kind of go to Celsius and stuff like that. But again, it is per gram of carbon. So that's why we know we should use this as our half-life here as 5730. So same deal, we're going to solve for K, which would be the natural log of 2 divided by the half-life here. And that's going to give us the natural log of 2 divided by 5730 years. And that will give us a decay constant of, make sure I don't miss any zeros here, 0.000121. Again, the units here are going to be years, right? Reciprocal years, basically. 1 over years, which is our first order, right? 1 over seconds. Now we have two numbers here. We have 4.5 disintegrations per minute per gram of carbon and 15.3 disintegrations per gram per carbon. You know, which one's which, right? So an ancient skull and a living guy. So much like life, right? Living is new. Yes. So that's your initial. And again, if you're ancient and you're probably not here anymore, that is going to be your final. Yeah. Also, right, it's radioactive decay. So the initial should have a higher counts per minute, if you will, or disintegrations per minute than something that's been around a while. So that's again another way you can look at that. So basically the natural log of our final, which is 4.5, equals the natural log of our initial, which is 15.3. Again, in terms of units for these guys, we're okay because they are both in the same units. So everything technically will cancel out correctly. That's going to be minus our decay constant we just solved for, and that's going to be T. So if we sort of clean up, we take the natural log of 4.5, we then subtract the natural log of 15.3. We get something like minus 1.22378 equals minus 0.000 years times T. Dividing our decay constant to the other side gets us a time of 10113 years. And if you want to clean it up, probably like 101 years. Yeah. So it's like 10,000 years old. So I think that classifies as pretty old. Yeah. Any questions on that calculation there? Again, still your basic first order kinetics. Again, you can see here, it doesn't have to be molarity or grams. Again, a rate of radioactive decay is a very sort of common one that you come across. So why don't you try another one here? So they found, let's see where they find here, a civilization that was 15,600 years old. If a living sample gives 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon in a piece of rice that was found on the site? So take a minute or so, see what you come up with. Okay, so this again is another decay problem. And we're going to need our equations. And again, the units here are slightly different. These are a little bit different than what we just saw. These are actually counts per minute per gram of carbon. Again, the per gram of carbon here is going to be important. That's going to tell us that we're going to use really the same half-life that we used here in the previous problem of 5730. And just like before, in this case, we're actually looking for, again, if a living sample gave us 20 counts per minute, that would be our initial. We know the time there of 15,600 years. We're actually looking for a sort of concentration. So just like before, we are going to need the decay constant. Since it is actually the exact same number as what we used previously, we're just going to jump in and kind of use the number. But again, we would do the same calculation here to figure out the decay constant as we did previously, and we'll get that 0.000121. So K in this case would be 0.000121 years. That gives us the natural log of A, which is what we're looking for, equals the natural log of our living, which will give us 20 counts per minute, minus our decay constant, which we would solve for the exact same way as we did in the previous problem. And in this case, our time is the 15,600. Again, in terms of time and our decay constant, we're okay because of the units are the same. Again, you do want to definitely watch those things, especially in these problems. You'll sometimes come across some different units. So we take natural log of 20, we subtract it from 0.000121 times 15,600. We will get the natural log of A equals, looks like 1.10813. We're going to take E of both sides, I believe. And that will give us a final one here. If I hit the right button and not that button, try that button. There we go. Of 3.03. Now the units here are going to match our original units, which are these. So the units here would be counts per minute per gram of carbon. Yeah. Also does make sense. Again, this sample is decaying over time. So the counts per minute should be a lot less, as that sample has been there for a lot longer period of time. It's gone through some half-lives perhaps. And obviously it should be giving off less radioactivity than our original kind of fresh sample, if you will. Any questions on that calculation there? So you can see here the practical application, right, is, you could figure out how long, say, the in and out double was on the ground that you found, all those good things, right? Any questions on any of that stuff? All right. So what we're going to talk about now is some of where the energy of, come back. There we go. Where the energy of fission comes from. So remember, a fission reaction essentially will involve a nucleus that will sort of break apart because it's unstable into usually two new nucleuses. And usually as a result of that, when a fission sort of reaction takes place, you got this unstable nucleus. Could be spontaneous. You could actually make it unstable by hitting it with a particle, but it's unstable. And it usually will again split off into a couple of new nucleuses. You'll get some neutrons that are sort of formed as well. And usually you'll get a lot of sort of energy that comes off sort of in this process as well. And one way that we could relate this is through Einstein's equation there, E equals mc squared. E is obviously our energy. M is our mass, and C is our speed of light, which again is our 3 times 10 to the 8 meters per second. Now, for example, as we talked about a little bit previously in this chapter as well, in comparison of a nuclear sort of reaction to a traditional, say, exothermic chemical reaction, there's a very big difference in the amount of energy that's produced. And as you can see there, if you take uranium 235, which again is sometimes used as fuel for, like, say, nuclear power plants and so forth, it produces about 1.7 times 10 to the 13 joules of energy. Um, and that's very much more energy than, say, an exothermic reaction that produces something like 10 to the 6 joules of energy. So you get a tremendously more energy produced. Again, as we talked about, this is because we are changing those protons, neutrons, and those sort of core particles that we find in the nucleus. And that's different than in a chemical reaction where it's really just those outside electrons that are involved in a reaction that's taking place. So this brings us to a couple of important things, and one important thing is something that's known as mass defect and what is sometimes referred to as binding energy. And when a nucleus forms, some of the mass of the separate nucleons, so when we talk about nucleons in sort of nuclear chemistry, it is pretty much what it sounds like. It is those particles that you find in the nucleus. So that's your protons and your neutrons, right? So those guys that you find in the nucleus. And some of the mass of those separate nucleons gets kind of converted into energy via this process. So when sort of a nucleus is made, or when a nucleus is broken apart, there's a certain amount of energy difference that occurs from the actual nucleus and basically the um, mass of all the particles that make up that nucleus. And that difference in mass that sort of gets converted into energy during this process is what is sometimes referred to as the mass defect. And the mass defect is that difference in energy from sort of the whole nucleus together and the parts that make it up, basically. And that gets turned into energy. And the energy that's released when we do form a nucleus is sometimes referred to as binding energy. So how this ties to Einstein's equation is that equals mc squared. This is what is sometimes referred to in this application as the mass defect. So when you calculate the mass defect in sort of Einstein's equation, you could use that, and then obviously the speed of light there to do the calculation. Now, there's also some alternative ways that you can sort of do these calculations that are really based off of Einstein's equation, but you could kind of use them almost as conversion factors, if you will. And one such example here is 1 mega electron volt equals 1.602 times 10 to minus 13 joules. And 1 AMU, a mass defect, equals 931.5 mega electron volts. So this is a way that you could kind of do the calculation without maybe using Einstein's equation, or you could use Einstein's equation as well, and you'll both get the same answer. And binding energy per nucleon is sometimes calculated. And the binding energy per nucleon is used for stability. So this is another big way that you could kind of look at stability of something. The greater the binding energy per nucleon, the greater the stability of that nucleus is. So the higher the binding energy per nucleon that you calculate, the more stable something is. So for example here, if we look at, say, fluorine 19, and fluorine 19 it basically has, as we could see there, it basically has 9 protons, and it would have 10 neutrons. And if we get that from obviously taking the mass number, which is the top number, 19, minus 9, which is the bottom number, which is the atomic number, and that gives us the 9 protons and the 9 neutrons. And we could calculate the mass defect, which is sometimes abbreviated a mass defect. By taking the mass of each of the particles that are there, so there's 9 protons, and if we look up the mass of a proton, it's 1.007825 AMU, and we add it to 10, which is how many neutrons we have in this case, and the neutron is 1.0086665. And as you remember, right, the mass of a neutron is the largest in terms of mass of all those particles, just barely beating out the proton. And the atomic mass of this isotope is 18.994 AMU. And if we do this conversion here, we will get 9 times 1.007825 plus 10 times 1.008665 minus our 18.9984. That's going to give us a mass defect of 0.1587 AMU. So this difference in mass is the difference between basically the mass of the isotope and basically the mass of the particles that make up basically that nucleus. And that's what's going to be converted really into energy. And again, there's 2 ways you could do it at this point. So I'm just going to kind of show you both ways. And again, you can kind of choose whichever way you sort of like. One approach would be at this point, you could use Einstein's equation, which is E equals mc squared. And again, this would be our mass defect. So if we put in our number, we would get 0.1587 AMU times our 3 times 10 to the 8 meters per second squared. And if we do that, we end up with 1.42. Where are we at here? There we go. 1.42 or 3. All right, try that again. 1.43 times 10 to the 16. Now the units here are AMU, meters squared, second squared. And this is close, but this is not really a unit of energy that we need. So we do need to do a conversion. And the conversion that we need to do is get rid of the AMU. And we're going to use this conversion here, which is 6.022 times 10 to the 26 AMU per kilogram. Yeah. And that is because 6.022 times 10 to the 23 is Avogadro's number, and that is per gram, basically, right? So kilogram would be 3 more, so that's why it's the 26. And if we do that, we will end up with 2.37 times 10 to the minus 11. The units now would be kilograms, meters squared, second squared. And perhaps you recognize those units as a kilogram, meters squared, second squared is the same as a joule. So that's why we have to do that conversion there where we kind of use Avogadro's number. And that gives us 2.37 times 10 to the minus 11 joules. Now we want to know a lot of times joules per nucleon. So nucleon is the protons and the neutrons. Essentially it's a mass number. So very common, what we would then do is take this and divide it by 19 nucleons. And that would get us 1.25 to the minus 12 joules per nucleon as the binding energy in joules per nucleon. Any questions on that approach there using Einstein's equation, which again is sort of one way that you could do it. Now, just to show you sort of an alternative approach and what those numbers that we saw on the last slide will allow you to do, which is essentially this without necessarily officially using Avogadro's number or the Einstein equation. You could take up to this point here and start with your 0.1587 AMU. And can use that conversion that we saw on the previous page that an AMU, a mass defect, equals 931.5 mega electron volts. Gets you something like 147.8 mega electron volts, which again is another common sort of conversion or unit that you find for binding energy. And you could also use the other conversion that was on that page to go from mega electron volts to joules, which is our 1.602 times 10 to the minus 13 joules. And if you do that, you end up with our 2.37 times 10 to the minus 11 joules, which as you can see is the same as what we got up there. You then obviously could divide it by the 19 nucleons, and it will get you up to this answer as well. So sort of those conversion factors that we saw on the previous slide, they really are based off Einstein's equation. And again, they just kind of short-rooted out without necessarily having to use Einstein's equation. And they're also very beneficial because, like I said, this is also a very common sort of unit of nuclear binding energy. And again, sometimes you'll even take this guy here and divide it by the 19 nucleons. And that would get you 7.78 mega electron volts per nucleon. So again, binding energy oftentimes displayed one of these two ways, either joules per nucleon or mega electron volts per nucleon. And again, you could do it either way. As you can see, they both get you to the exact same answer when it's all said and done. But it's just sort of your preference. So you could even do the conversions and get yourself the joules if you need joules, or again, if you need mega electron volts, you could do it that way. You could also, again, use Einstein's equation and then use this conversion here to go from joules to mega electron volts if you kind of need to go backwards as well. Any questions on that calculation? So again, that slight difference in mass here of the protons and neutrons that make up the nucleus and the actual atomic mass of that particular isotope, again, going to be converted into energy in this process, which again is sort of that nuclear binding energy. Any questions on that calculation? All right, so why don't you try one here as I go through here, and that shows us what we just did. Got the same number, which is good. Actually, let's take a look at this first before you get to that example. Again, this is a chart, and again, you can use nuclear binding energy per nucleon as sort of a measure of stability. And again, the higher the nuclear binding energy per nucleon, the more stable something is. And pretty much the most stable is right about there. Iron 56 is sort of the most stable nucleus. Again, you can see it's sort of the top of that peak there, and it has sort of the highest nuclear binding energy per nucleon. Here's another picture in case you didn't like the first one, but again, you can still see iron 56 there up on top. All right, so why don't you give this a go here, some numbers that you might need, I think, yeah. So why don't you calculate the mass defect here and the nuclear binding energy in mega electron volts per nucleon, yeah? So take a minute or so, see what you come up with. Okay, so let's take a look here. So again, you could kind of do it either way you like. But first thing you want to start off with, obviously, is we have carbon 16. Remember, 16 is the number. We go to the periodic table, we see carbon's atomic number is 6. That should tell us that it has, in terms of protons, 6. In terms of neutrons, right, 16 minus 6, which gets you 10. So again, we want to figure out the mass defect here. So the mass defect is going to equal our 6 times the mass of our protons, which is 1.00783 AMU, added to the mass of the 10 neutrons, which is 1.00866 AMU. We're going to subtract it from the atomic mass of our isotope, which is given to you here, and that is 16.014701. Love atomic masses. They have thousands of numbers here. All right. So 6 times 1.00783 plus 10 times 1.00866 minus 16.014701. That's going to give us a mass defect here of 0.1189 AMU. Again, at this point, you could, if you wanted to, use Einstein's equation, or again, since we're looking for mega electron volts here, it may just be easier to use that conversion that we saw, which it really is based off of it anyways. And AMU is 931.5 mega electron volts, and gets us about 110.7 mega electron volts. Remember, we do want it per nucleon, so that essentially is your mass number. So we're going to take this and divide by 16 nucleons, and we will end up with a grand total of 6.921 mega electron volts per nucleon. Again, if you wanted joules, you could use Einstein's equation. That will get you sort of joules directly. Or again, you could use the 1.602 to the minus 13 there as that conversion factor to get to joules. Any question on that calculation there, where any of the numbers came from or anything? All right, you got one more here to go. So see what you come up with. Calculate the binding energy per nucleon for iron 56 that has a mass of 55.93494. Let's do it. Let's mix it up. Let's do it in both mega electron volts per nucleon. And why don't you also figure out what it is in joules per nucleon? So why don't you do both? All right, take a moment and figure those out. Okay, so again, we want to start with the iron 56. We go to periodic table, atomic numbers 26. So that's going to tell us we have 26 protons. Again, in terms of neutrons, 56 minus 26 going to give us 30 neutrons. So again, we want to start with our mass defect, which is that difference in mass. And we're going to take our 26 protons. We're going to times it by the atomic mass of a proton, which is our 1.00. We got there 783. Going to add it to our 30 neutrons, which each are 1.00866 AMU. Again, we're going to subtract it from the atomic mass of the isotope, which is 55.93494 AMU. And that's going to give us a number. Let's see here. It's going to give us 26, 1.00783 plus 30 times 1.00866 minus 55.93494. That's a lot of numbers. 0.5284. Again, here at this point, you do have two ways you could do it. You could use those conversions. You can, again, go into Einstein's equation if you like to. So I'm just going to continue probably with the conversions here. Again, 1 AMU, a mass defect, going to be our 931.5 mega electron volts there. And that will get us 492.2 mega electron volts. If we want joules as well at this point, actually we could just, let's do it this way first. We'll do one thing here first. Since one of the things we're looking for is mega electron volts per nucleon, we could just divide this number here by our 56 nucleons. And that would get us 8.790 mega electron volts per nucleon. And if we wanted joules, we could use our conversion factor as well that we saw there. And again, a mega electron volt is 1.602 times 10 to the minus 13 joules. And that would get us 1.41 times 10 to the minus 12 joules per nucleon now. And again, if you took the E equals MC squared approach, you'd probably end up here first, and then you could use the conversion to go up there. Any questions on the calculation there? Now, as I mentioned before, we could use the nuclear bonding energy per nucleon as a measure of stability. So, for example, here, if we look at our iron 56, we have 8.79 mega electron volts per nucleon. If we compare it to the ones we did previously, so carbon 16, 6.921. And if we even go all the way back to that first one we were playing with there, which was our fluorine, I think, right? And our fluorine, oops. And for our fluorine, what do we get there? 7.78 for our fluorine. So our fluorine was 7.78 mega electron volts per nucleon. Again, you could use these to look at stability, and the most stable here, as we saw in that graph, is our iron 56 at 8.7, followed by our fluorine, right, at 7, and then our carbon 16 at 6.9. So again, this is another way that you can look at stability, is like comparing the nuclear binding energy per nucleon. Again, the higher the binding energy per nucleon, the more stable it is. Any questions on that there? Obviously, you would want to compare them when the same units, right? All right, let's continue then. So how do we sort of generate different elements, or make elements sort of go through a fission process? Sometimes it's what is referred to as nuclear transmutation. So one way that we could kind of make something unstable is to bombard it with a particle. And one way that you could do that is through a particle accelerator, like what we see on the screen. Essentially, it has a magnetic field and basically gets the particle spinning very fast, obviously. And then you basically shoot it out as target. Obviously, when these things get hit with these particles, they're not very happy, and they then obviously split off into some new nucleuses and obviously produce some particles along the way as well. Here's what is sometimes referred to as nuclear transmutation, the transuranium ions. A lot of these guys are on the bottom. This is really how we oftentimes will sort of generate some of those man-made, if you will, elements like Einsteinium, Nobelium, and all those type of things. Again, through this sort of bombarding of these guys with some type of particle. As you can see here on this list, sometimes the neutron, sometimes the alpha particles, sometimes you're hitting it with the, combining it with another sort of isotope as well. And that leads us to nuclear fission. And again, nuclear fission that happens in sort of a non-spontaneous way. There is spontaneous fission, as we talked about a little bit earlier, where it just sort of spontaneously will break apart into new nucleuses and some neutrons. Nuclear fission is sometimes done by starting this by hitting it with a particle. So uranium-235, which again is sometimes used as fuel in a nuclear sort of reaction, if you bombard it with a neutron, which is what we got coming in here, it hits our uranium-235. It becomes very unhappy and looks like a bowling pin, right? Becomes uranium-236, which is unstable. And then typically what will happen is it will go through fission, which means it basically will split off into some new nucleuses, as we see here. And again, those new nucleuses will usually be accompanied by some more neutrons that get basically developed in this process. And this process also generates this right here, a ton of energy. So you can see if you take uranium-235 and you go through this sort of fission process, you basically will generate 2 times 10 to the 13 joules per mole of uranium-235. And that is, a lot more energy given off than, say, if you did the combustion of coal, for example. And the comparison here is really one that we'll talk about just a little bit as well. That is basically how power plants sort of work. So power plants essentially are your traditional power plants where they burn something like coal to use the energy, basically for power, as opposed to, say, a nuclear power plant, which uses, obviously, is a fission reaction like what we see on the screen here, which also produces energy as well. So that's why sometimes people will say nuclear power a little bit more efficient, because obviously you get a lot more energy out in that process than you do in a traditional power plant. But obviously there's drawbacks to both, as we'll talk about in just a second here as well. Now, the products that we get in these fission reactions are not always the same two products that are made. And again, you can see here sort of these peaks. These are sort of the common representative fission products that we get as a result of this this fission reaction with uranium. And again, not always the exact same two guys that will come out. But what is usually fairly consistent is the idea that it does generate neutrons, and it obviously does generate a lot of energy. But again, the identity of these guys that come out not necessarily always the exact same 2 every single time. And this sort of fission reaction is important because the way it sort of starts and what is produced in a fission reaction can make it sort of continue to occur. And when you have a fission reaction such as this that is basically self-sustaining, that is what is referred to sometimes as a nuclear chain reaction. And essentially, if you think about sort of this fission reaction, the thing that sort of kicks it all off is a neutron. And what you get when you do this reaction is a bunch of neutrons that are made, which means that they can then just go and start doing this reaction over and over again. And you're basically making, as a product, the starting material basically for this reaction. And that's why in a nuclear chain reaction, it could kind of continue to grow exponentially, right? So this reaction just continues to occur. And in order, though, for this reaction really to be self-sustained, you do need a minimum amount of what's known as the fissionable material. So you need what is known as the critical mass in terms of the amount of uranium that's necessary to basically keep this reaction continuing. And if you do hit that critical mass, which is what we see over here in this picture, again, that is where you're going to get basically this reaction to be able to really self-sustain itself, continue to grow again exponentially. Every time that thing goes through that fission reaction, in addition to those neutrons that are being produced, you're producing a tremendous amount of energy every time that occurs. You're also producing a lot of radioactive products, right? Those 2 elements that are made, a lot of those radioactive products that also hang around a very, very long time. If you keep the critical mass under that, so non-critical like we have on the left-hand side of the screen there, the reaction will still be able to sort of propagate, but again, it won't be able to sort of sustain itself. It will still do some damage, but obviously it won't continue to build sort of that exponentially. And in sort of a nuclear bomb sort of situation here, we have sort of a subcritical mass separated from each other. But obviously when this hits, the explosion, right, will kind of take our triangle wedge into here. And now what you have is essentially a critical mass of something like uranium-235, which will be able to obviously continue this sort of chain reaction. And like I said, obviously a ton of energy, a ton of radioactive products that are being made, and it continues happens, all bad things, right? But you can use sort of this fission reaction for, normal sort of things that are so necessarily bad in certain senses. And that is basically like a nuclear reactor or a nuclear power plant. So basically a power plant, both a traditional power plant and a nuclear power plant. They both work really the same way. They basically have water. And you heat the water. When you heat the water, right, you get steam. Steam goes out to the turbines, to the generators, right? And you get lights, right, which is good. Lights turn on and all that good stuff. So really the main difference sort of in a nuclear power plant versus a traditional power plant is sort of how they heat the water. So in a traditional power plant, a lot of times they would use coal and burn coal, which is again why that coal comparison was there earlier. And that coal, the heat from the energy from the coal would heat the water, obviously, and you get the steam and all that good stuff. In a traditional nuclear power plant, they use a fission reaction that involves uranium. And the heat that is generated from this nuclear fission reaction is used to heat the water and create the steam and all that good stuff as well. And so why in a nuclear power plant, is it sort of safe-ish to do that? They usually obviously will keep the radioactive part a little bit separated from sort of the water supply. So in here, we have a couple of things. We have fuel rods. fuel rods really have these like little pellets of uranium, almost like eraser, pencil eraser sort of size. And those are what are used basically for the fission reaction. But when the fission reaction occurs, obviously there's some water in here. This water is in an insulated sort of container that's used to heat this bigger source of water. And this reaction happens, and obviously all the radioactive parts sort of stays together here, right, as it goes through. The steam again goes out there to the turbine. And usually they will also have other things in there, which are known as control rods. And what the control rods are these guys that are sort of things that are sort of coated in things like cadmium, so forth. And what they are neutron absorbers. And neutron absorbers are really good because if you think about the fission reaction, what starts the fission reaction, what's generated in a fission reaction, as we saw over here, is the neutrons. Yeah. So the neutrons are needed to kind of continue this reaction, to continue to grow. So what these control rods essentially do is they kind of grab out these neutrons. And obviously, if they grab out these neutrons, they're not available to continue this reaction to occur. And thus, you could kind of keep the reaction under control. The other major thing that they do as well, obviously, is they keep the mass of uranium under critical mass. So even if something did happen, there wouldn't be enough product to keep that reaction sort of going. Usually these guys are sort of separated from each other, right? And for example, in San Onofre, right, that's as close as the one we got, I think. You have those big domes, right? They're usually encased in those very, very big domes. Usually nuclear power plants are also near a big body of water, which is off the coast, right? And that's because as you use the steam, right, and use some water to cool down the steam, you're basically kind of recycling the water, right? So you take the steam, kind of cool it down with some water, and back it in goes, and you get this sort of cycle where you could kind of do that. Now, again, there's a lot of good and bad with both, obviously, in a nuclear power plant. Some of the bad is obviously it produces all this sort of nuclear waste, right? Which has things that have half-lives for a very, very long time. And you need to figure out a place to store it, a place to keep it in, and all those type of things. So it's not necessarily clean in that sense. While a traditional power plant where they burn coal obviously makes a lot of pollutants in the air. So obviously there's some downside to that as well. Here's sort of a comparison of that. Again, traditional power plant, you kind of produce these sort of pollutants. But again, in a nuclear power plant, you have a lot of that nuclear waste that again basically hangs around a very, very long time. And that's what we sometimes refer to as spent fuel. So sort of the products that are made as a result of these nuclear reactions, they're sometimes referred to as spent fuel. And the problem with those things is they themselves, as you can see here, this is basically the storage time in years, like 10 to the 3 years, right? So you come right in this area, you're looking at, what's that, like a couple thousand years. These things, for how long you got to kind of store them for, right? So that's a very, very long time to figure out where to store them, how to store them, who keeps track of it for all those years. So again, that's this problem sort of with nuclear power plants as well. And for a lot of years, they would just kind of store all this stuff on site because nobody wanted any of that stuff in their area. I think a while back they opened up somewhere in Vegas, but in Nevada, where they sort of store all this stuff now and stuff like that. So, or started to use it at least. So there's positives and negatives of both. But that's again the major difference there between them. So that brings us to nuclear fusion, and fusion is a little bit different than fission. So in a fission reaction, we sort of bombard something, becomes unstable, the nucleus splits off. In a fusion reaction, we basically take two small nucleuses and combine them to one nucleus. And that usually happens at very high temperatures. So we take two guys and kind of make one, and it happens at very, very high temperatures, like your vacation on the sun high temperatures. So that hot um, requires a lot of heat and energy for this sort of fusion reaction to occur, to kind of fuse those two nucleuses together. Now, we also oftentimes will use, radioactive particles and stuff for medicine. And obviously, if you think about it, for medicine, we definitely would want something with a small half-life. You don't want something with years and years in terms of the half-life. Otherwise, your follow-up appointment would be fairly long down the road. So usually hours, maybe minutes, sometimes a day or so, maybe in terms of half-lives. Again, but nothing usually very long in terms of half-life is used. We can use radioactive sort of particles and all sort of aspects. A lot of times they will use it for some type of test, some imaging, as you see here is a brain image. Again, the nice thing about radioactive isotopes that in the body, they perform the same way as a normal element, if you will, a non-radioactive element. But what you can do, obviously, is you do some type of scan for the radioactivity. And as you can see, it sort of highlights everything in a scan. Also, you could directly use sort of radioactive particles for sort of to shrink things like tumors and stuff like that. They used to, and I think they still do, implant sometimes radioactive sort of pellets and tumors and stuff like that to try to shrink them and stuff like that. So, it can be used obviously in a wide area of medicine, some of which we may hear about a little bit later on here in a half hour. And again, here's just some more examples of it. And obviously, a shorter half-life is definitely what you would want to use. When we do use anything that's radioactive, we usually oftentimes use a Geiger counter. And a Geiger counter basically, it's like a wand with a little voltage type thing, and it basically will make a sound, and it will beep if you come across something that's radioactive. It'll beep very loudly if it's obviously a lot of radioactivity, maybe not so much if there's not a lot. But usually you'll use it if you are using radioactive materials. You'll use it to, when you start, probably after you're done cleaning up, just to make sure everything's good. In the laboratory as well, usually you'll have to use, a lot of times they used to make you wear rings and like badges. Years ago, they used to be more like x-rays type film in it, and they would develop it every so often to see how much you have been exposed to. But I think they use a little bit something slightly different now than what they used to use. But if we use a Geiger counter, for example, though, if we just kind of hold it up in the air, it will go off. It won't go off hopefully loud, but it would make some noise. And that's because there really is background radiation, all around us. And, you'll hear it beep and stuff like that. So it usually won't be completely silent. You'll usually hear some background radiation. If it beeps a lot, that's not so good, obviously. And there's a couple of different ways that we sort of measure the effect of radiation on people as well. One is what is known as a RAD, as a radiation absorbed dose, and one's a REM. And basically, a REM is sort of, your exposure level. It does depend on the type of radioactive particle that's happening. So you can see, you basically take a RAD times a quality factor, and you can see a gamma ray is 1, a beta ray is 1, and an alpha is 20. So again, the alpha particle, if you remember, doesn't travel as far as, say, the gamma, which travels very far. And we are exposed, as you can see here in this table, to a variety of sort of radiation doses, from X-rays, air travel, nuclear waste, I guess how close you live to where they test weapons and that type of stuff. So, we do get exposed to some of that. Obviously, in terms of exposure, when we ever around radioactive stuff, it's important not to be obviously around it for a long period of time. It should obviously, like as we talked about at the beginning of this chapter, make sure you figure out what is the proper safety equipment that you should be wearing. Do you need shields? Do you need gloves? Obviously, what type of protective equipment that you need if you are working with something. Again, it is going to be different based on the emitter, but more protection is usually best, and limiting exposure is obviously extremely important as well. And that should wrap this chapter as well. Any questions on this chapter here, which is chapter 21? All right, so let's talk a little bit about what's going on. So today I started about 11:30. We'll have lab, so make sure you come through the lab entrance. and we will do our presentations and through that order that I put up there up on Canvas. So we saw that. Again, you should have the ability to share your screen, your PowerPoint presentation. You obviously can open your microphone and speak, and your video, if you would like to be seen as well, you can do that as well. So you should have all that available to you when you come through. I will, I think, sometime today post up online as well a quiz on this chapter. So you'll take a quiz on this chapter. It'll be a something you could download. You could kind of work it out, and you could upload it when you're done. It will count towards a quiz, a real quiz. Since we didn't take too many this semester, this should help, I hope. And you'll have some time to do that as well. So it'll be on this chapter here, nuclear chemistry, and that should hopefully help out for the quiz part of it. We got one more lecture to go on Thursday as well, and that we'll talk about organic chemistry. And believe it or not, we covered everything actually at that point. No, quiz will not be due today, so I'll give you. It'll be due. Honestly, you could turn it up, I think, until next Tuesday. I'll give you a week. It'll be like a take-home quiz type of thing. So that should give you plenty of time to do that. So, but it'll be posted up sometime today, I think. And again, it'll be on this chapter and stuff like that. And who knows, maybe towards the end of the week, we might have one more, like a review type quiz that you also can maybe take home, obviously, and turn in as well. I don't know if I have anything specific for the final. Obviously, you could use the previous stuff for those chapters. And I think up online, there should be, if not, I'll double check some stuff for these last few chapters and stuff like that. No, in terms of the paper, you could submit one paper per group, since it was a group project. You don't need to submit two separate ones. I'm assuming they're going to be pretty much the same. Unless you did write two separate ones, you can. But I think it's said on there that you can submit one paper per group, if I'm not mistaken. No, that was done on purpose. I was taking down the, I did take down the grades, so you can't see the grades anymore. They'll be up there as well later today as well. I was just catching up on some grading, so later today, when I get a chance, I'm going to put it all back up there. And I graded some of those lab reports and obviously your exams and all that kind of stuff. But I just took it down because sometimes it'll keep giving you notifications as I'm grading and stuff like that to annoy you. So I just took it down to get it all kind of, so we'll keep getting that. So probably later today as well, all the grades will be back up there, including the lab reports and the exam and all that kind of stuff. And again, I did take it down, so it's not just your Canvas. It should be down for everybody, I think. Any other questions on that? So next week, again, is finals. So we should have, I think, a lab final on Tuesday, and I think one lecture final on Thursday, if I'm not mistaken. And obviously those will occur during the times that they are scheduled. So we'll continue to that so nobody has any type of conflict with anything. All right, any questions on anything? All right, so we'll start lab about 11:30. And I don't know off the top of my head, to be honest with you. So whatever time it says on the syllabus, we obviously will keep to those scheduled times for the final. So off the top of my head, I don't know. I almost want to say it's 10:30 on one of them, and then I don't remember when the other time is, to be honest with you. It might be a little bit later or earlier, but whatever it says on there. Yeah, I'll send out an announcement for sure towards the end of the week when I look at it for sure. Any other questions? Okay, so again, get ready for your presentations and all that good stuff. Come through the lab meeting. And again, we'll talk about sort of the presentations and some things at the beginning, and then we'll kind of get into it, okay? All right, I'll see everybody in about 20 minutes or so.